Hello and very good morning to all of you. Today this discussion and the subject is strength of material. So we are discussing the topic of bending moment and shear force. Next to this we will be discussing how to draw the bending moment diagram and the shear force diagram. So here we are discussing only the basic fundamentals of this chapter. First of all, we will discuss what is a shearing force and what is a bending moment. So for this you should know what is shearing. Shearing is nothing but slipping of a surface with respect to other when you apply the force like this. It is slipping. So when you cut a piece of paper with the help of scissors, plates or simply with hands, what you do is you shear one surface with respect to other. This is slipping, shearing. You all must have played the game of carom board. So if you put the uh, these black and white pieces one over another and strike with the help of the striker, then from the base, the one piece which is in contact with the ground, that is the one at the base, that goes out. So as a result, we say that it has been sheared out. So similarly here I have shown what is shear. Suppose this was a intact body and we applied the force like this with the help of say scissors or hands or any other force. This force, these equal forces are acting on it. As a result, it is getting sheared at the surface, which I have shown in red. So this new surface is produced, which is called the shear surface. So it is moving one in upward, other in downward direction. Similarly, this was a rivet. All the mechanical engineering students are quite familiar with rivet. So it is used to join two plates, maybe more than two plates in case of riveted joints. So when this rivet, I have not shown the plates in between this. It is joining two plates, one and the other below this. So when the force is applied to the plates, this force is applied on the plates like this. So this is the shearing force. Now as a result, one part remains here, the other moves, and this surface, it has been sheared along the surface which has been shown in red. So this is the basic of shearing. Now come to the beam. This is the beam. The types of beam we will be discussing later on. Now the loads which are acting on the beam, they are point loads W1, W2, W3. There are three loads and these two are the points of support of the beam, and R1, R2 are the reactions which are acting here at the point of supports. So in equilibrium, net forces must be equal to 0. Net force means net upward force or downward force in any direction, net force must be equal to 0. Similarly, there is no horizontal force acting on this beam, so it is in equilibrium. W1 plus W2 plus W3 is equal to R1 plus R2, and the beam is in equilibrium. Now I take a plane here. This plane you can take anywhere. I am taking this plane here, vertical plane. On the left side of this plane, the forces acting are W1 and W3 in downward direction, R1 in upward direction. And on the right side of this, we have W2 in downward, R2 in upward direction. So the resultant of these forces, this may be acting in the upward direction. It is not necessary that it is always acting in the upward direction. This is for the purpose of explaining that suppose the resultant of these forces, this and this is acting in upward direction, this is equal to F. So on the other hand, on the other side of the plane, the resultant of the remaining forces, that if they are on the right side, this is on the left side. W2 and R2, the resultant force is F, and this should act in the downward direction for the purpose of equilibrium. So force F is acting to the left side of the plane in the upward direction, and an equal force is acting in the downward direction on the right side for the purpose of equilibrium. So this force, what these forces are trying to do? These are trying to make this portion that is on the left side of the beam slip with respect to the portion on the right side of the beam like this. This portion is moving up, this portion is moving down. If the shear force on this side is in downward direction, this force will be in upward direction, and the movement will be reversed. This part will move down, this part will move down. So this is called the shear force. And the moment of the forces That is, if I take the moment of the forces on the left side with respect to this plane. This plane is called shear plane. Let me show this. This is shear plane, about which the body is getting shear, or there is slipping of one part of the body with respect to the other part. So this is shear force concept. This is the concept of shear force. It is not necessary that always shear force on this side will be upward and this side will be down. Now if I take the moments of all the forces, I have shown the distances of all the forces with respect to this plane. Actually, we have to find the shear force and the bending moment of the forces which are acting on the beam. So shear force we have found. On this side, the shear force is F in the upward direction, and for the equilibrium, this is equal to R1 minus W1 minus W3. And on this side, this is in downward direction, so this is downward force minus upward force W2 on this side. If I take the moment of all the forces on the left side about this plane, then the moment will be, I will take this in, that is clockwise direction as well. So this is the convention we have shown here. This convention is that the force here in this direction, this is positive, and this sense is taken as negative, and this is called sagging. If the bending moment is such that it tries to make this beam in this shape, this is called the sag, like sag present in chain. And this type is called hogging, so this is taken as positive and this is taken as negative. So bending moment of this R1 about this plane will be R1 multiplied by distance A from the plane. This is positive. Similarly, we have the bending moment of W1 about this plane is W1 multiplied by distance B, it will be negative. W3 is also having a negative moment, W3 multiplied by C. So this is the bending moment of the forces on the left side of this plane with respect to this shear. Similarly, the moment of these forces on the right side can be taken. So this is about the shear force and the bending moment. Now let us come to the types of supports of the beam. This is a very important concept. So we have generally roller support and hinge support, and we also have the fixed beam. So what is roller support? This is roller support. Now the special thing about this roller support is the reaction is always acting in the normal direction to the beam if we use the roller support. The beam is having an additional degree of freedom so that it can move in this direction. It can move if we have a roller support. So it can be lifted off its position, it can move in horizontal direction, so the reaction is always in the vertical direction, normal to the beam. Then we have the hinge support. Hinge joint, like we have this joint here is hinged. So it can move only in one direction, only 1 degree of freedom, rotation is possible. So if we have a hinge joint in the beam, this is the load acting on the beam, the reaction will be always inclined. So if we have this reaction R1 here, it is having two components, R1 in y direction and R1 in x direction, taking this as x, this as y direction. So if you have a load which is acting on the beam, suppose the load is inclined, the load is like this, it will be have two components, vertical and horizontal. So this vertical component will be balanced by the vertical reaction in upward y direction, and this horizontal component will be balanced by this horizontal reaction. If there is vertical load only, in that case there will be no horizontal reaction acting on the beam. If we have horizontal load acting on the beam only, then we have only the horizontal reaction, no vertical reaction. This is called the hinge support. Generally we have this type of support, roller on one side and hinge on the other side of the beam. So these are decided according to the type of motion required or type of degree of freedoms required in the beam. Then we have the types of beam. These are the beams which are generally used. The beams can also be curved beams, and we also have horizontal and vertical beams, etc. Inclined beams. So as you know, the vertical beams generally they are known as the columns and the struts. So that is a separate topic. So we have horizontal beams, inclined beams, etc., curved beams, and vertical beams. So here we are discussing only the horizontal beams. We have simply supported beam. That means the beam is simply supported at 2 points. It is just kept at 2 points. So these are the points, and the load is acting in the downward direction. So the reactions are present here, and this is because of the load plus the own weight of the beam. Generally, in the numerical problems which you solve, it will be given that weight of the beam is negligible as compared to the external load acting on it. So we leave it. But beams also have their own load. In most of the cases, you will find this like the span created by the beams on the bridges, long bridges. It's a long or short, whatever type of bridge it is. And in our houses also, we use the beams for the purpose of load support. So this is simply supported beam, which has been simply kept at these 2 points. Then we have fixed beam. The 2 ends are fixed inside the wall, this side and this side. So here we are having the normal reactions. These are the vertical reactions because of the load which is acting here, W in downward direction, and along with this we have the fixing moment on the 2 sides of the beam. Now what is a fixing moment? This I will discuss. Let us take the example of a simple cantilever. What is a cantilever? Cantilever we have discussed. One end of this is free and another end is fixed in the wall. So if W is the load acting here, in that case it is having a normal reaction acting at the other end plus a fixing moment. Now let me discuss what is this fixing moment. When a cantilever is having a load W acting here, then L is the length of the cantilever. Now for the purpose of the equilibrium of this cantilever, the net downward force must be balanced by the net upward force. Here we cannot have reaction, and this point is, this end is not supported. Whole of the beam is unsupported except at this point where we have this fixed beam which has been built. So a normal reaction acts here in upward direction, and we have R equal to W. This is the reaction which balances this load W in the downward direction. And what this load is trying to do, we can take the example of our hand. If I put a load here, weight here, it may be a point load, it may be a uniformly distributed load, non-uniformly distributed load. So the resultant is acting at the center of gravity of the load direction. So point load here. This load is trying to move my hand in the downward direction. If I do not consider this hinge joint, I consider this as a straight beam. Okay, this is a hinge joint, so we are not considering this. So this is moving the hand in downward direction. So what I will have to do for the purpose of equilibrium, a load must be acting here in upward direction so that it can balance this. So this is called the fixing reaction. And this load about this point is creating a moment. So load W into L. W into L about this point, this is having in this direction a moment. So it means that this beam is trying to, this load is trying to rotate the beam in this direction with respect to this point. Now to balance this moment, a moment which is called fixing moment acts naturally at the point of this where it has been fixed in direction opposite to this. So fixing moment is opposite to this moment. The moment created by this is in this direction. So naturally a moment acts in this direction. It is called fixing moment, which is opposite to the moment W into L. This is called the fixing moment. So this type of fixing moment present everywhere whenever we have a fixed beam, be it cantilever or it is a fixed beam. Then we have continuous beam supported at more than 2 points is called a continuous beam, and we have this overhanging beam supported at 2 points similar to this, but the important thing here is these two ends of the beam, they are overhanging out of the total length of the beam. So these are the types of the beams which generally we have. Apart from this, we have statically determinate and statically indeterminate type of beams. So statically determinate beam means the problem can be solved statically determinate and indeterminate. If you can solve the problem by using the concepts, simple concepts of statics, that is, the net forces acting on the beam are in equilibrium net forces. Sum of the all the forces in a direction is zero. Sum of the moments is zero. These are the conditions of equilibrium. If you can solve the problem by this, then it is called statically determinate. If you cannot solve this, then it is called statically indeterminate. As in this type of problem, the principles of this statically determinate beam are not applicable, and all others can be solved by using statically determinate methods. Then come to the types of load. First of all, we have point load. It means that the load is acting only at a point. The load is acting on a very small area that can be called as the point, and we show this with the help of the arrow. It may be up or downward reactions, point loads, and the vertical loads in downward direction, maybe in upward direction, maybe inclined also. These are called point loads. Then we have the uniformly distributed load. It is shown here in this manner, can be shown with the help of arrows also, acting in downward, maybe in upward direction also, and its intensity here is varying uniformly, small w per unit length. Like in case of we have the beams inside big walls over which there is a wall. So wall can be considered as a uniformly distributed load of the beam. Then we have non-uniformly distributed load, also known as uniformly varying load. So the intensity of load distribution is varying load. Here it is 0, and here at the other end it may be W per unit of length. So the rate of variation may be constant. Here it is, variation is uniform. It may be non-uniform also, such that the pattern of this variation of load may be parabolic or may be cubical parabolic also, and this we will discuss when we will be solving the numerical problems. And we also have the beams on which a moment is present, only a moment is present, or a couple is present. So M0 is the couple which is acting at any point along the length of the beam, in clockwise or anti-clockwise direction, and we also have the moment which is varying in the same manner as this. This is constant moment, this is variable moment. Here the moment is 0, it is increasing in this direction, and here we have a moment which is having magnitude m0 per unit length. So for these types of beams, we will be discussing in the next discussion how to find the shear, how to draw the shear force at the bending moment diagrams, apart from the relation between the shear force and the rate of load distribution, and also shear force and the rate of variation of bending moment. So this is all for today. Thank you.